And here's chapter 3 of microbiology. So this is a big one, 3 parts. Let's begin looking at the cell. So cells come in all shapes and sizes. There are many different kinds of cells. Some cells are living on their own. Some cells are part of a multicellular organism and are specialized, but we're going to concentrate on basically the difference between prokaryotic and eukaryotic cells in this chapter. So this is just a nice overview. This is Giardia lamblia, which just causes giardiasis. This is a protist. You can see it has flagella to move around. This is a bacterial image of rod-shaped or bacillus-shaped bacteria. This one here is of a larger protist, looking at the vacuoles inside. This guy here these are red blood cells, human red blood cells, and then this guy is trypanosome. So it's another protist, and it infects the blood, as you can see. These are spirochetes that spiral, kind of like fusilli pasta, really. And I'm not sure what these are. These are a different kind of protist. So lots of different kinds of cells. And again, a little bit of history here. So you want to explain how these individuals try to prove or disprove spontaneous generation, right? So spontaneous generation was the idea that you can just have life come from non-living things, right? Which is not true, because the cell theory now states that all living things all cells arise from other cells. You need a living cell in order to have another cell. So we're going to start off with von Helmont here. We looked at him in chapter 1, I think, and he was a proponent of abiogenesis or spontaneous generation, right? So he supported it. And he thought that, cheese and bread wrapped in rags and left in a dark corner were able to produce mice. And after several weeks, there were mice in rags. Many people, like basically everybody, believed in it because there weren't anything to prove otherwise. There was no microscope to see the cell. So science, it was in its very, very beginnings here. And he actually did this experiment, which I think is kind of funny. Got some dirty shirts, he got some wheat, waited about 21 days, and then he saw mice. So therefore, mice comes from that combo. These guys, Reddy, Needham, and Spallanzani, you want to know what they did. We did cover Reddy already, but we'll go over this again. So Reddy's experiment, he wanted to disprove spontaneous generation. He didn't think it was correct. So we know that Reddy and red meat, right? He had a container of meat open to the air, and flies came in and made maggots. He had a sealed jar where no maggots formed, and then he has a gauze covered jar where air, remember, people thought that air was really important. It had a life force in the air, could get in, and which was the idea that, oh, this jar didn't have air, that's why nothing grew, because air contained a vital force. This experiment showed that air can get through, and the maggots were on top and not from the meat. Okay, so you'd think that this is a pretty good showing of how maggots don't come right from the meat. However, it was very early on, and this did not change everybody's opinion on spontaneous generation, but it was the first to sort of work in that direction. Needham was opposite. So Needham wanted to prove that spontaneous generation was real, and everybody knew that boiling things at this point would kill organisms, but he prepared like broths. These are usually chicken broth or meat broth. He boiled them, and he showed that, hey, when we boil them, there's no longer microbes, but then if you let it sit for a while, you do get cells. Now you might be confused because it's corked, right? But this was a very loose cork, and air was able to get in, and so you have cells arising after that, right? He thinks that this proved his theory of abiogenesis, that the broth did regrow those cells. Spallanzani didn't like that. So Spallanzani and Needham were working at the same time, and he did an experiment where he just basically did the same thing that Needham did, but he boiled the flask a little bit longer. He sealed it tightly. So he fused it so there was absolutely no air coming in. And so you see that no cells grew. And in this experiment, he proved that Needham was wrong and life did not spontaneously generate, and bacteria had to have come from the outside world, the air. And Needham said, oh no, you boiled it too long. You spoiled the vegetative power by boiling, so there's some kind of life that exists in the broth that he boiled away. And so that was Needham's comeback. So Spallanzani did a different experiment, and he did different boiling times. So he said, okay, if I boiled it too long, let's just see at every single one of these time points what happens, right? He left them partially sealed. The partially sealed, some were partially sealed like he did, and some were hermetically sealed, so as he did in his previous experiment, so no air can get in. And he hypothesized that more boiling should lead to less life, and he left some jars, like Needham had, as leaky to ensure that the active principle was not damaged. And what he showed was basically that when there was a tight seal, no matter how long you boiled it, you did not have any bacteria growing or growth of anything. They didn't know it was bacteria. And then the loose seal had growth. So he basically wanted to prove that boiling did not damage the broth's ability to support life, and that is actually the seal. You have to seal it in order for life to not occur. So he thought like this would really prove that the contamination arose from the air, contamination from the air. So that experiment occurred. Did anything really change the scientific community's idea of spontaneous generation? Not really. So you still had some mixed opinions about that. We know that Louis Pasteur was the one that really sort of put the, I guess, final nail in the coffin with his experiment. So we want to basically know his experiment. And we talked about this before, right? So he's French. There's actually a Pasteur Institute in France, in his honor. So he created a very unique swan neck feature. So he had to create this flask to prevent entry of any heavy particles that might contaminate the broth, right? And there are two parts to it. So he both sterilized the broth with fire. Then what he did was he had one S-shaped flask with that curve, and then he broke off the other one. And the neck of the flask, obviously microorganisms could grow in this because they fell right into the broth. And then in this S-shaped curve, you could argue that air had plenty of opportunity to get in, but because the particles were heavier, they settled down here and the broth was sterile. So pretty interesting experiment here. And it basically helped really prove that abiogenesis was incorrect and that there is something else happening to grow microbes. Then we have Lister and Koch. They both were also active in microbiology. Lister developed procedures for proper care of surgical wounds, and then Koch established the microbe to disease, which is now called the germ theory of disease. So very different from miasma, very different from abiogenesis, was that there are certain particles out there called germs, and they cause a specific disease. For Lister, just to sort of go on a little bit more, he really was the father of antiseptic surgery. So imagine being in war, or you're working in the fields, you have a major accident, you're basically very hurt, and you go into surgery, and doctors at that time didn't realize that you had to wash your hands, that surgery had to be clean, and patients would die of not of their surgical wounds, but the infection after their surgery. 50% of patients on average were dying of their post-surgery infections, which is a huge number. So Lister knew the work of Semmelweis and Pasteur, And he insisted, so he was thinking, oh, well, if things are in the air that can contaminate substances, right, we need to be clean. So we need to wash our hands and have extreme cleanliness during surgery. And then he further went on to use chemicals to sort of clean the area, right? Carbolic acid, which is known as phenol, and then spray disinfectant or antiseptic during surgery. So interesting thing, like Listerine is probably named after this man over here. So this is a surgery, and it did improve the survival rates of the people who underwent surgery. So Lister. And then again, we covered Koch's postulates in a previous lecture, but just to go over it again, this is the control where he had a healthy organism. He took the blood of a healthy organism. He looked at the blood, didn't see anything funny, and plated it and did not find any causative agents or bacteria in the blood. But when you have a diseased organism, and again, this was anthrax, he saw an agent, right, a suspected agent. There's something in the bloodstream. He plated it, something grew on the plate, and then he put the bacteria that grew into a healthy mouse. The healthy mouse, sorry guy, died of the disease, and then he pulled the causative agent out of the dead mouse. So basically what he proved was the microbe that he put into the mouse, the healthy mouse, is the same microbe that he can cultivate after the mouse died. And he also showed that the disease organism, the first one and the second one, had very similar, identical, basically, symptoms, and that the disease must have been the same causative agent that was inoculated, taken from the inoculation here, or culture here, inoculated, and we have the causative agent. So this Koch's postulates is actually used in the same way today when you want to figure out what is causing a particular disease. A little bit more sophisticated, probably. All right, so in terms of the timeline of these sort of microbiological advances, we have our Francesco Redi a long time ago, right, in the 1600s, that wanted to disprove spontaneous generation. Then we have Needham, almost 100 years later, saying, wait, I think spontaneous generation is correct. Spallanzani, right, wanted to disprove Needham, so they were in a tit for tat. Needham saying spontaneous generation is correct, and Spallanzani saying no. And then finally, we have our big Louis Pasteur, who did his S-shaped flask experiment and really just settled on the fact that there was no spontaneous generation, right? That it had to be from the air. In this timeline, we have just a couple more people here. We looked at Hooke, right? We looked at Hooke, and he saw cells under the microscope. Van Leeuwenhoek also saw single-celled organisms under a microscope, right? So we have a microscope being utilized here to see the small world that we can't see with our naked eye. And then we have our, we don't cover Snow, but he was another person. And then we have Pasteur's S-shaped flask experiment, and Lister showing that there indeed are contaminants in the air, and then when you clean things, you have better survival rates. And then we have Koch's postulates, which he basically grew a microbe, put it back into an animal, and showed that it caused the same disease. So it took a while. If you look at the dates here, right, we go from 1600s to the 1900s. Really took a long time to really shift the scientific community into the microbial world. One note here is that Pasteur, as I mentioned in the other chapter, was known for pasteurization. So the way that we kill most microbes in milk, right? Anything that's pasteurized was invented by him. So he saw that when microbes enter something and they ferment, they can actually spoil beer and wine. And he's French, so the French were actually really worried about the spoilage in beer and wine. They're a wine loving country. So he was put to work really to figure out how to get the wine spoilage down. And he figured out that if you heat the liquid up to a certain temperature to kill most of the microbes, that you can keep the substance longer. All right, so that is it for part 1.